So I'd like to just discuss this in the context of a problem that I've been looking at recently, which is how to characterize the workhorse algorithm of deep learning, which is stochastic gradient descent. Okay, so to start, let me just take the simplest problem, which is linear regression. So imagine that you have a set of points on a plane, and you have many points. So you have a data set, so you have p points, 2 coordinates, and you would like to fit this point with a line. So in principle, you would like to find the parameters m and q that fit at best your data. So how do? You can set up some empirical risk minimization problem. So you define the empirical risk, I call it the Hamiltonian, which is just the distance between the actual values of these labels, so mu, minus the ones that you can estimate with the current estimate of m and q, okay? And so you would like to find m and q that minimize this cost. So for this problem, so this cost is a convex function, so it's easy to find the minimizer. But one way to do it algorithmically is just doing gradient descent. So you initialize the values of m and q some way, and then you just run these dynamics, okay? And this brings you to the unique minimizer of the Hamiltonian. So this is a low-dimensional problem. You have just 2 parameters to be found, and you are under-parameterized in the sense that you have many points and just few parameters. Now, what happened? So this is, by the way, how science works. And what happened in the last 10 years is that this paradigm has been extended into high dimension. So now you replace the points by pictures, and you have cats and dogs. This is the Alice and Bob of machine learning. And so these pictures are high dimensional. And what you would like to find is a function that assigns the right label to each picture. So you have a data set, and now you have labels y mu, and you have high dimensional vectors xi mu that represent the values of the pixels of each image, and you would like to find a rule that fits this data. And now there is no reason why this data should be on some line, so typically what you would like to consider is a nonlinear function f. And this function depends on some parameters, w's. And how do you find the best set of parameters? Well, again, you set up an empirical risk minimization problem. So this is your Hamiltonian. It's the actual value of your labels minus the ones that you estimate given the weight vector w. And so you'd like just to minimize this function. And now if this function, this cost function, so if f is nonlinear, this function is non-convex, so it will have in general many minimizer, and there is no way you can find them analytically. So how do? The simplest thing is to run gradient descent. So you assign some initial configuration for these weights, and then you just run these dynamics. And these dynamics will bring you to a local minimum of your cost function. Now, all this is done in high dimension because the dimension of this picture is big, the number of data points that you have is big, and the dimension of this weight vector is big. So all the paradigm of statistical learning here actually fails because this is done in high dimension. So I will not enter into the details of all this. There is a huge literature that is developing. So what I'd like to do is to consider a small problem, which is a computational problem. So how do you do, so what is gradient descent? So I would like to focus on the training algorithm, so the algorithm that gives you the weights. So you have this Hamiltonian, you can write it this way, so it's just a sum over the data points that you have in your data set of some local cost function. And now the gradient is just written in terms of a sum over all the data points of some local gradient. And now the computation of this thing can be done. There is an algorithm that is called backpropagation. It's some linear algebra algorithm. It's expensive, but it's inevitable. And then the thing that makes the algorithm very expensive is just this sum. Okay, so typically you have a huge data set, so you would like to perform this huge sum, and this is very impractical. So nobody is able to run it in real data sets with real images and so on. So how did people come to a solution? They developed stochastic gradient descent. So the idea is the following. So imagine that you have your data set. You can decompose it into mini batches. Each mini batch contains a portion of the data set. And now you replace the full gradient with a gradient computed only in the mini batch. Okay, so you just perform this sum on a restricted portion of your data set. And then what you do is that you so first of all, the data points that belong to each portion are random, and the way in which you give a mini batch to the dynamics is random. So you have some kind of randomness in the dynamics. So in the end, you have a noisy algorithm. And this algorithm is interesting. There is no Lyapunov function, so there is no way you can understand this in terms of optimization of a cost, because there are no guarantees. And you know that, you see that it's a kind of driven algorithm. There is some kind of information flow, because typically you can expect that there are mini batches that contain more information than others. For example, you can have a mini batch in which the images are very clear and some other in which the images are more blurred. So, but this is the only thing that you can do. And whatever task you do in machine learning, whatever learning problems you take, this is the algorithm that people use. So data sets, neural network architectures, everything changes except this algorithm. This is really the thing that people use. And this algorithm works, okay? And to me, it's kind of unexpected. And so the question is, why this is so? And is the noise that you introduce in the algorithm helpful for optimization? So these are kind of important questions and represent part of what we would like to understand in machine learning. And what I'd like to do in this talk is to really focus on the algorithm. And what I would like to do is to develop some dynamical mean field theory to study the performances of SGD in a prototypical hard high-dimensional optimization problem. Okay, so what will be missing is what actually is very interesting, for example, real architectures, real data structures, and things like that. So I'd really like to focus on the algorithm. Okay, so how do I do? So I need to develop some theory, some setting in which I can define some learning problem. And so statistical physics started to look at these problems back in the 80s. There were first works by Hopfield, who essentially developed a theory for associative memories. But this theory then turned out to be very important for neuroscience. And then in a parallel stream of works, actually, that are relevant for this talk, there were a set of works that were very influential by Elizabeth Gardner and Bernard Derrida. So in this first work, Gardner essentially was interested in simple architectures of neural networks. She wanted to understand what is the space of interaction, the space of synaptic weights leading to some task. And then she visited the IPhT, and she did with Bernard Derrida these two very influential works. And what I would like to do, so I will not enter into the details of this work, but I would like just to focus on this one, because in this work, essentially they set up a kind of way of thinking to learning problems that I'd like to show. So it's a kind of setting which is of Bayesian nature, and it's called nowadays the teacher-student setting. And so this is not a model that they defined, but the line of reasoning is exactly the one that they proposed. So imagine to define the following model. So imagine that you have a vector x star. This is n-dimensional, and I'd like just to fix its normalization this way. So I call this vector the signal or ground truth or the teacher. Okay. Now I define a set of random matrices, J mu. Each random matrix is n-dimensional, and n is going to infinity. It's the high-dimensional limit. And these matrices are symmetric. They have entries that are Gaussian, zero mean and unit variance. And how many matrices do I have? I have order n matrices, and I have a proportionality factor alpha, which is a control parameter of order 1. It's called sample complexity. And now you can think about these matrices as the images of your data set. And now I need to produce the labels. So how do I do it? I just define this rule. Okay, so I just take this sum. So this is an object of order 1. It's a random object. But now I have some labels, and I can construct a data set. Because now I have the images and their labels, and they are correlated through this rule. Okay? And now the question is, can I learn this data set? And in particular, can I find back the vector x star. So imagine that I just give you the labels and the matrices. Can I find back the vector x star that I used to produce their correlation? Okay, so how do I do? I define some empirical loss. It's the Hamiltonian. It's just the expected distance between the labels and what I estimate. Now you see that this is not x star, it's my estimation of x star, so it's x. And so I'd like to minimize this cost function. Now this is a high dimensional, it's non-convex, and so it's the natural setting. So there are two regimes depending on how many data points I have per degree of freedom. So there is a regime which is over-parameterized, which means that alpha is less than 1. So in this regime I have a kind of, so the loss landscape is a kind of canyon landscape. You have a zero energy manifold because, I mean, you have more degrees of freedom than data points, so you can fit all your data set. And this is the regime that is really relevant for deep learning. And then there is another regime in which I have more data points than degree of freedom, and this is called underparameterized. And in this case, I can have a kind of rough energy landscape. You can have plenty of minima, and I will focus on this regime because this provides a prototypical hard dimensional optimization problem where I can benchmark my algorithms. So why it's hard? Because typically you expect that you have exponentially many minima in the dimension of the system. Okay, so let's focus on this regime. So there are two ways you can try to understand this cost function. One is thermodynamics, and you in particular can focus on the ground state. And this was done by Fyodorov in 2018, and who studied this model. And actually thermodynamics here is very easy in the sense that there are just two ground states. One is x star and one is minus x star because this cost function is Z2 invariant. And these two ground states are simple. Okay, in statistical physics terms, they're called replica symmetric. So this is very easy. Now the question is whether the algorithms can find back this ground state. And since this is high dimensional and convex and non-convex, you can expect some glassiness there, which may hamper the performances of the algorithm. Okay, so we started the analysis of stochastic gradient descent, and this was done with Persia Kamali. So again, we have some empirical loss. This is the expression of the local losses for each data point, and then we can define either gradient descent. This is the discrete time version. I have eta, which is the time step. So here I have the computation of the full batch gradient, and this is stochastic gradient descent. So now I need to define some way to define a mini batch. So how do? I just consider some selection variables as mu that are 0 with probability 1 minus b and 1 with probability b. So what is the role of these variables is that just to select what are the data points that I consider in the computation in my approximation of the gradient. Okay? So this algorithm is a discrete time algorithm. There is no way you can define a continuous time limit unless you define some dynamics for these variables S mu, which can be done. But I will really consider a discrete time algorithm. Okay, so how can you analyze this algorithm? Where you do dynamical mean-field theory, and in order to do this, you do path integrals, which is the thing that we all like. And the standard technique that has been developed here is the Martin Sijarros Janssen de Dominicis formalism. These are the two papers that I think Henri was referring to yesterday by Cyrano de Dominicis. So you apply this technique to this problem, and you get a set of dynamical order parameters. And these parameters are just correlation functions that tell you, for example, what is the similarity between two configurations during the dynamics at time t and t prime. You have a response function that tells you how much the trajectory of your system changes if you apply some perturbation at a previous time. And then the most important dynamical order parameter is the magnetization. So in this setting, the magnetization is it's just the projection of x on the signal, on the ground truth. So this actually is a measure on how much you are close to the ground state. And in particular, if you are able to recover the teacher, it means that you have found a fully magnetized system. So learning here in this context is equivalent to say that you have a ferromagnetic system. So this is the quantity that we really need to monitor. So there is a way to write some equations in the high dimensional limit for these control parameters, for these dynamical order parameters, and these are the equations. So they look complex, but actually they can be integrated very efficiently, and they have a lot of structure. And the simplest way to write them is just use superfields. So you have some two-point correlation functions that encodes both correlation and response functions. And this two-point correlation function satisfy a Dyson equation, and the books where I learned all this when I was a student in Rome were these two that you recognize. And so this Dyson equation depends on some kinetic term, and then you have some self-energy. And this self-energy is proportional to a coupling constant, and what is the coupling constant here is the sample complexity. So how many data points you have per degree of freedom. And of course, it doesn't make any sense to consider the small coupling constant limit because, I mean, we would like to have many data points. So we need to really solve this equation numerically. And OK, so this is the result. So this is the magnetization as a function of time for two algorithms. One is stochastic gradient descent with batch size b equal to 0.1, and the other one is gradient descent. Okay. So let me focus on this yellow line and this blue line. So these two are the performances of these two algorithms for sample complexity alpha equal to 3. So I have 3 data points per degree of freedom. And you see that SGD is much faster than GD. So note that here I have a log scale. So it's much faster to recover the ground truth, to go to the ground state. So this is the first conclusion. And now let me just try to see what happens if I decrease the sample complexity. So I give you less data points, so the problem becomes more complex. And so you can expect that it takes more time to find the ground state. And now the question is, how much more time? So you expect that these curves shift to the right when I decrease alpha, but then you see that the rate at which the gradient descent algorithm shifts to the right is much larger than the SGD. Okay? So the question now is it really better SGD with respect to GD? And what I mean by better, so you can expect that at some point the time it takes to go to the ground state will diverge. And this depends on this control parameter, this sample complexity alpha. So if I decrease alpha, at some point the time it takes to magnetize will really diverge. And now, is this point the same for the two algorithms or not? Okay, so you can measure this relaxation time to the ground state. And this purple line is what happens if you look at gradient descent. So you see that it diverges at some point. And this point, you can fit it with some power law, So you can fit the point where the algorithm doesn't manage to find back the ground state. And this is at this value of the sample complexity. And this is what happens if you take stochastic gradient descent. And you see that at the value where you get the divergence for gradient descent, SGD has a perfectly finite relaxation time. So this means that SGD has a noise which is very helpful to optimization. Okay, so I think I can stop. So what I wanted to say is that we can do a theory for SGD. We just started. There are plenty of questions that are still unanswered, and we constructed mainly the tools. We can just establish that SGD is significantly better than GD, and this is, I think, a non-trivial statement, because for SGD there is no, I mean, you can expect that noise in optimization algorithm is typically helpful. This is the lesson from simulated annealing. But here there is no Lyapunov function, so you are not guaranteed at all that this algorithm is going to do something interesting. And it does, okay. And so now the question is if we can do a theory for the recovery threshold, and this is in principle possible. What we need to do is to understand what are the configurations that are visited by the algorithm, And the algorithm is a non-equilibrium algorithm. So it drives the dynamics, so it prevents fully relaxational dynamics, so it drives the system to some kind of non-equilibrium stationary state, which is characterized by interrupted aging. And so what you need to do in order to construct a theory for the recovery transition is to develop a kind of microscopic fluctuation theory, because at that point you have huge fluctuations that brings the system to the ground state. And okay, so I think that I can conclude just by saying that statistical physics has been very influential, and now it's really shaping modern high-dimensional statistics and theory of deep learning. And I just presented something on algorithms, but the same kind of ideas that were really pushed forward by Gardner and Derrida are very modern, and they are very actively studied. So I'll stop here. Thank you.
So there are plenty of questions. Should we send this big mic? Yeah. Start with Henri and then on the back.
Why don't you use simple Langevin dynamics instead of the gradient dynamics? Because that would be the most natural generalization, no?
Yeah, it's just that it's so I just looked at.
No, I understand, but why don't people in general use?
Because it's hard. Because in the Langevin case, you need to compute the full batch gradient, and so this is just hard to do. So if you do Langevin, you should compute the full batch gradient plus adding noise. So they just don't add noise and assume that the mini batch gradient, this stochastic gradient, has enough noise that it's good.
Or something like you're not sure that you get you go to a non-equilibrium stationary state
in the SGD case.
Yes.
No, you do. I'm not showing you data, but actually, if you look, for example, to correlation functions, so when you go to large times, essentially you go to some time translational invariant state, which is out of equilibrium.
I see.
And it's really the phenomenology is really the one of interrupted aging, because essentially you have some relaxation time, which is the typical time where you see more or less the same mini batch, and then it drifts towards other mini batches. So in this typical time, you are effectively doing gradient descent. So you expect some aging dynamics, and then this aging dynamics is interrupted because there is some drive.
Okay, thanks.
There's a question by Bérangère.
Yes, maybe it's very stupid, but is the total landscape made by each landscape of individual mini batch equal to the total landscape? Because if yes, then SGD is just a way to go out of minimum. But
yeah, so one way in which you can understand this is that actually so this landscape is really the full Hamiltonian, and now when you cut the Hamiltonian, well, I mean, this changes in a chaotic way, so you can have like barriers that are erased or things like that. So in principle you can do it this way, but it's unclear how to implement this in a practical thing. So to me, this just looks like some dynamics. So thinking this way is too complicated.
Yes, there are plenty of quadratic functions in your computations. You normalize x, your cost function, the action of j, and in fact, in large dimensions, the spherical geometry is a very peculiar one. I mean, if you change, instead of normalizing by sum of x's square x equals 1, you normalize by the maximum of x equals 1, one of the x's equals 1, it might change. Isn't it possible that there is some kind of very strong a priori on the data and all that in all the computation?
Yeah. So the thing is that, so this setting is very artificial, and I totally agree. The main point of this, I think, is that, So from machine learning point of view, people were not sure that, for example, SGD and GD were different. Okay, so this is an example in which you can clearly see that they are totally different. But then, I mean, that this kind of behavior and in a quantitative way is related to any real problem, I mean, this is to be done. But the fair answer is that the form of the Hamiltonian that I chose and the model is such that you can do all the analysis. And I mean, doing that is not clear because in this kind of problems you have typically huge finite size effects. So having something which you can really write the equation is good.
Other question for Pierfrancesco? Yes. Gregory, up. Oof.
Thanks. So, hopefully not too stupid question, but maybe completely off. Don't hesitate to tell me. Machine learning has a notion of overfitting because you have essentially lots of parameters. How does that fit in this picture?
Okay, so this would be this case, which
Yeah,
are not...
yeah, definitely.
So because in this case you are really overfitting your data. Now the question, now we are looking at this case, which would provide a more natural setting because in a real setting typically the loss goes to 0 and you overfit your data. And then what you would like to do is to redo the same analysis in this case and try to see how SGD, for example, where it lands on this canyon and what are the regions of this canyon that lead to better generalization. And it's known, for example, that if you do GD and SGD, you can go to bad regions. So you can engineer algorithms to go to bad regions, and people don't do that. So they go to good regions. So we wanted just to explore this in this case. But for the moment, so what I wanted really to do is to benchmark the algorithm. So and to benchmark it, I need to define a hard optimization problem. So here it's kind of easier because I have many minima and zero averages. Here I have just 2 in a dimension.
Thanks.
Other questions for Pierfrancesco? Well, if not, let's thank the speaker again.